All right, so our exponential function is always in the same format. What is that format?
Y equals a to the x.
Right, so it's always going to be y equals a times b to the x, all right? Y equals a times b to the x. So we're just going to fill in our x and y's. Now, they gave us our initial right here. So they actually gave us our initial. Anytime your x is 0, you have your initial condition, which is your a. You automatically know your a if they give you 0 as an x value. Because if you plug in a 0 for x, that's a 1. Plug in the 24 for y, you're going to get a equals 24. So as soon as they give you a 0 number, you automatically know that a is 24. You don't have to solve for it. All right? And then we're going to use that with our other values. So we're going to say our new function then is going to be y equals 24 b to the x. All right? So really all we have to solve for is 24. So we're going to plug in these numbers. We're going to plug in a 3 for x and an 8/9 for y. So we have 8/9 equals 24 b to the third power. All right. So how do I solve for b? Divide by 24. We want to divide by 24. All right. And so if I divide by 24, it's 8/9 times 1/24 equals b cubed. And I'm going to, cross cancel here. So my 8 and 24 cross cancel, right? With 1 and 3, right? So I get 1/27 equals b cubed. And now I can take my cubed root of both sides. Cubed root of 1, any root of 1 is just 1. What's the cubed root of 27? 3. So b is 1/3. And so the function that I am looking for is going to be y equals my a, which is 24, times 1/3 to the x power. So we have a formula here. My formula for continuously compounding is a equals p e to the rt. Okay? And we're really just plugging it in here. We're solving for a. That's the amount in our account. P is my principal. My principal is how much I initially invested, so that's 400. Times e to the r. My rate is 7.6%, so that's 0.076. My years is 1.5. So you literally just have to plug it in your calculators, right? You want to make sure that you have the 0.076 times the 1.5 all in the exponent form here. If not, it's going to do the exponent first and then that multiplication of the 1.5. So make sure you put it in your calculators correctly. But when you do, you should get rounded to the nearest cent, 448.30. So let's talk about what logarithms are. We have been doing exponential functions. Exponential functions means I have an x in my exponent. I have a variable in the exponent position. Logarithmic functions are just the inverse of exponential functions. So what do I mean by inverse? It undoes it, all right? So for example, if I have addition, the inverse of addition is subtraction. If I have multiplication, the inverse of multiplication is division. It just reverses what you're doing. And so in an exponential function, I am looking for the exponent. So if I'll say, 27 equals 3 to the x, right? That was 3. And in a logarithmic, it's just written where your answer is the exponent. And so in a logarithmic function, your base represents the base in an exponent. Your number that you're taking the log of represents what that number is to the power. And then your answer is the power you're looking for. And so they basically they're inverses of each other and they will counteract each other, meaning a logarithm will cancel out an exponential base and an exponential base will cancel out a logarithm because they are inverses of each other. If I were to take 3 and multiply by 2 and then divide by 2, I would end up with 3 where I started from. And that's what logarithms and exponential functions do to each other. Okay, they are inverses of each other. All right, the first thing they start out with is just talking about exponential type functions. And you can see the Richter scale here is an exponential function. And so they show you here that we have a magnitude of 0 times 30 times 30 times 30 times 30. And when you look at what it looks like, the Richter scale is a base number times 30 to a power. And that power is based on how much energy is released. Energy is released in an earthquake, okay? And so using exponents, you have to remember your exponential properties. So the first example that they give us here is with an earthquake. In 1995, an earthquake in Mexico registered 8.0 on the Richter scale. In 2001, an earthquake of magnitude 6.8 shook Washington state. Compare the amounts of energy released in the two earthquakes. And so for this one, we're going to compare the energy released in the 8.0 to the energy released in the 6.8. And so all they're reminding you here is what you do with exponential properties. My e's would cancel here. If I have like bases, what do I do with my exponents?
Subtract.
Yeah, I just subtract. So I'm going to have 30 to the 1.2. If I put that into a calculator, the energy just difference is 59.2. So the earthquake in Mexico released 59 times as much energy as the earthquake in Washington. You can see how exponential functions affect it greatly. It was just from an 8 to a 6.8. It was just a 1.2 difference. But that was a 1.2 difference exponentially. It was 59 times more energy. That is a big difference if you are standing in the middle of an earthquake, all right? And so that's, exponential functions do that. Exponential functions change it dramatically, not just linear. And so they're trying to just re-emphasize what exponential functions do. So now let's look at logarithmic functions. Look at the top of page 439. What is a logarithm function, all right? The logarithm to the base b of a positive number y is defined as follows. All right, and they give us this. We are used to this, right? This first one here. We have some number equals a number to a power. We have been doing these. We have been doing exponential functions. Y equals b to the x. This should look very much like all of the exponential functions from the prior sections that we did homework with. Y equals b to the x. That is an exponential function. If this part is true, think about your logic from geometry, if-then statements. If this is true, then you can write that function as a logarithm. And the way you would write it as a logarithm is the base of your exponent becomes the base of your logarithm. That's the number base you are talking about, all right? The number that the base to the power equals is what you're looking at with your log. So log of a number is what the base would be taken to the power and equal. And we're going to rewrite some of these. And then your exponent here is the number you are looking for. So if you put into your calculator the log of some number, it's going to tell you the exponent that number would be taken to. Now we're going to explain the logarithms on your calculator in a minute because there are two basic logarithms on your calculator. They have specific bases, okay? But first we're just going to be rewriting these so that you can see how we can rewrite them. So let's look at this first example, example 1. They want us to write 25 equals 5 squared in logarithmic form. We all know that 5 squared is 25, right? That's easy enough. Now we're going to rewrite it in log form. So in log form, I would say the log then, base 5. 5 would be the base of my logarithm of 25. So the log base 5 of 25 equals 2. What I am saying there is 5 to some power equals 25. That's what logarithms are doing. They're saying the base is your number base. The number you're taking the log of is what happens when you take that base to a power. And your answer is the power you took it to get there. All right? So we are simply rewriting an exponential function as a logarithm. The base of my exponent is the base of my logarithm. What that base is taken to to get to is what I'm putting here. And the exponent is the number I'm looking for to get it to that number. All right? So your base is your base of your log. Your answer is your number that fits with your base, and it equals the exponent. So rewrite these three. Check understanding 2. All you're doing is rewriting them. You're rewriting them from exponential form to log form. For the first one, you should have had log base 3 of 729 equals 6. Log base 3 of 729 equals 6. B. Log base 1/2 of 1/8 equals 3. It's okay if you have, it's equal, so it doesn't matter which side it's on. So you could have written it, because it's an equal sign, you could have written it, which is how I would have written it. Log base 1/2 of 1/8 equals 3. And then the last one, log base 10 of 1 equals 0. So log base 10 of 1 equals 0. So then if you have bases that nicely go to something, you can evaluate it without a calculator. You have been doing this, you did it in bell work. You basically were evaluating exponents without using a calculator. You were just saying, oh, 3 to what power equals 27? That's 3, right? And so that's what you're doing when they have a nice, pretty base like these do. If you look at this first one here, we have log base 8 of 16, and I always just say that equals x, because that's what I'm solving for. All right? Now, as a logarithm, it's not very easy to solve with just figuring out logically what's happening. But if you rewrite it as an exponent, then you can see what's happening. And so I am actually going to rewrite this back into exponential form. I'm going to go backwards. So think about exponential form. Log base b of y equals x can be written as b to the x equals y. All right, so I'm going to rewrite this. I'm going to say b, that's 8, to the x power, that's my exponent, equals my y, 16. Now, 8 to a power does not equal anything, but they have common bases, all right? They have common bases. 2 can be taken to a power to get 8, and 2 can be taken to a power to get 16, all right? So 2 to what power equals 8? So 2 to the third, that's 8, right? And then 16 is 2 to the fourth, right? Does everybody see that? So I can rewrite them as a common base. They have common bases. And with properties of exponents, I have a power to a power. What do I have here? 2 to the what? 2 to the 3 times x. Right, I'm just going to write it like that. And 2 to the fourth. Yes? Now, anytime you have a base to a power equals a base to a power, it means that those powers must equal each other, right? Because I would never have something like, oh, well, 2 squared equals 2 cubed. That's not true. 2 squared doesn't equal 2 cubed. In order, if I have the same bases, the exponents must be the same for that equation to be true. And so I have the same bases, which means 3x must be equal to 4. That's the only way this equation will work, if 3x equals 4. So how do I solve for what x is? Divide by 3. So x is 4/3, which means, way back up here, log base 8 of 16 is 4/3. So that means if I take 8 to the 4/3 power, I will get 16. Let's see if it works. Let's put it right here. 8 to the 4/3 power equals 16. What is 4/3? That's a fraction. I can rewrite that as a radical, can't I? That is the cubed root of 8 taken to the fourth power. Yes? My denominator is my index, my numerator is my exponent. What is the cubed root of 8? 2. What is 2 to the fourth power? 16. And yes, it works. That is to check it. So x equals 4/3. Terminology, common logarithm. A common logarithm is a log that uses a base 10, all right? So on your calculators, you see just the word log. So think of this as, if I have x, what's the exponent on that x? 1, it's understood. If I have the square root of x, what's the index on that radical? 2, it's understood. When I have log with no base, it is an understood 10, okay? So if you just see the word log, like on your calculator, or in a book, it means log base 10. So in your calculators, if you put in log base 10 of 100, which is what we just did for C, you should get 2. 10 to the second power equals 100. If you say log of -5, however, it will say error, because you cannot take 10 to any power and get -5.
Not really.
All right? If you say log of 0.1, that is 1/10, you will get -1, because log to the -1 equals 1/10. Okay? That is what a common log is. On your calculator, it is going to give you a common log, meaning always base 10. So on your calculator, unless you go into the menu and you rechange your bases, you're not going to do base 3, base 4, base 5 with log. There's a way to do change of base. We're going to learn it. But you're not just going to plug in a log and just tell it what base to do. It's going to do base 10. That is an understood base for your common log. All right, I just want to show you the graphs. We're not going to graph them. Remember, your exponential function shoots up. This is a base 10. So if I have 10 to the 0 power, I'm going to get 1. 10 to the first power, I'm going to get 10. 10 to the second power, I will get way up here 100, which is off this graph. The inverse, the logarithmic function, remember your inverses reflect across y equals x. So if you take that exponential function, you flip it across here, you get this right here. And this is what your exponential function looks like compared to your logarithmic function. They are inverses of each other. Your x and y is flip-flop places. That's what it means by inverse, okay? Remember when we solve for inverse, switch x and y, solve for y? That's what would happen with these as well, all right? So turn to page 446 in your books. We're going to talk about properties of logarithms. We are going to do these properties, and it's almost like simplifying when you learn exponents and variables. Like terms, you can simplify by adding them. With logarithms, there are things you can do. They are called expanding and condensing. This will help you when you start solving logarithmic equations, all right? And so we're going to learn these and we're going to show how to do them, but it looks like we're not going anywhere with them. It's because you're going to use them later to solve, okay? And so if you have a log and it has multiplication within it, all right, so one of ours had a fraction within it, which was division, multiplication. So let's say you have log of base whatever of one number times another or one variable times another. You can actually break it up into multiple logarithms. So the log of base b of m times n is the same thing as taking the log of m and adding it to the log of n. You can split it up into multiple logs with addition. If there's a product multiplication in here, this is called the product property. If it is division, you can split it up into individual logs with subtraction. This is called the quotient property. And if it is taken to a power, so let's say you have the log of something taken to a power, you can actually take that exponent and put it out in front like a coefficient. All right? And so these are some ways that you can start manipulating your logarithms to help solve for them. And you can go from one logarithm to multiple logarithms, that's expanding, or you can condense it, meaning you can go from multiple logarithms down to one, that's condensing. So let's look at these examples. We're just going to identify the properties. They went from log base 2 of 8 minus log base 2 of 4 to log base 2 of 2. What property did they use to do that? Subtraction condenses how? With what? With division. So they did this property. Well, if it's subtraction, I can condense it to one logarithm using division. 8 divided by 4 is 2. All right? Let's look at this one. So the first thing they did here, this is which property says x cubed times xy? Yeah. Well, the first property they use is probably product because the power only applies to the x. So the first property they used is my product rule. If I have multiplication, I can break it up into addition here. That was my product rule. Yes? And then they use the power rule. So they actually use two of them because this is a power and I can bring it out in front. So they use two properties here. They use the product rule and the property rule. And the power rule here. All right? So let's do A and B. Go ahead and really quickly figure out which properties they use there. All right, so the first one, they went from addition to multiplication. What rule did they use? I just said it. Products, right? So they use the product rule. All right, what about the next one? Subtraction, they condensed that with the quotient rule, right? And then these threes went up as exponents in the power rule, right? So power property and quotient property for that one, product property for the first one. All right? Let's look at actually doing these. Write each logarithm as a single logarithm. They want us to condense these into one logarithm, all right? The first thing that has to be true is they have to have the same base. You'll notice it said base B, base B. If it is not the same base, you cannot condense them, all right? They have to have the same base. Then we're going to look at the fact that it is subtraction here. It is subtraction. So I can condense these using what property? The quotient rule. So I can say, well, I can write it as 1 using the quotient rule, 20 over 4. So if I simplify that, it would be log of what? 5. All right. Let's look at B. When you have multiple ones, you want to do it in an order that makes sense, okay? So if I have this right here, I'm going to put it as an exponent first before I condense it with the other one that's over there. So you want to condense within it first and then condense with something else. So what rule tells me I can do something with this 3? The power rule. So I can write that as log base 2 of x cubed plus log base 2 of y. And then this addition tells me I can do what? Multiplication. So product rule, x cubed y. And so that's going to be 1 log. 1 log, they have base 2s. I can condense them with the power rule and the product rule. Go ahead and try A and B. All right, so for the first one, you could have taken 3 to the power, 2 cubed, multiplied that by 4, and then divided by 16. So you should have gotten 1 log, this is the common log, log base 10 of 2, because it's common log of 2. Can you write 3 log base 2 of 9 minus log base 6 of 9 as a single logarithm, yes or no? No, you cannot, because they do not have the same base. Does anybody need to see this one right here? Okay, so I'm going to condense this part, log 2 cubed. I'm going to bring that up. Then I'm going to multiply these. So I have log of 2 cubed times 4. And then I'm going to divide log of 2 cubed times 4 divided by 16. When you take 2 cubed, that's 8. 8 times 4 is 32. 32 divided by 16 is 2. So for these, they want me to expand it as much as possible. We want individual logarithms. And so I'm going to look at this and I'm going to say, well, this is division. So how can I expand division? With subtraction. So I'm going to say log, we're going to keep the same base 5 of x minus log base 5 of y. That's as much as I can do. Okay? Look at the next one. I have 3 times r to the 4th power. By the way, don't do the power unless it applies to the whole thing. Expand with the product rule first and then do the power. So product rule first, this is log, common log, so log base 10 of 3 plus log of r to the 4th. I can expand one more time. I'm not done here. I can do this power rule. Log of 3 plus 4 log of r. Check your work. You can expand the first one with the product rule. Log base 2 of 7 plus log base 2 of b. The second one, this one you would do the power rule first because it applies to both of them. Or you could say y squared over 3 squared. But it's going to be 2 log of y minus 2 log of 3. That exponent applies to both of them when it's in the parentheses. Okay? And then the last one, we can expand with both product and exponent. 3 log base 7 of a plus 4 log base 7 of b. They had individual exponents that applied to each of them.